Hello everybody. So this is chapter 3 for the Top Hat organic textbook. So we're going to be talking about some of the basics of organic reactions. We're not going to get into specifics, but mostly just looking at the general types. How about that? So there's 4 basic reactions that we're going to be dealing with. How about that? So the first one is substitution reaction. So here is where atoms get swapped between two. So in this case, we'll have the so this bromine here, right, gets swapped with the OH that's right there. So here's the bromine here. So this leaves. This is what's called a leaving group. It's going to go ahead and leave like that, and the OH is going to swap in for it. The other type is going to be elimination, and this is where the molecule itself breaks apart. And so what ends up happening is you lose a molecule of HBr. So that's what the minus HBr means. So you could also write it like HBr, like that. And what's left behind is a carbon-carbon double bond. So we're going to be going over that. I think it's chapter 8. For elimination type reactions. And whenever you think about elimination, you should probably think about making a double bond. The other type is an addition, where in this case, right, so two molecules are coming together to make one new one. So just the opposite of elimination, if we're going to put HBr across the double bond, H is going to be on one side and Br is going to be on the other. And the last one is just a simple rearrangement, where the molecule itself, the atoms just remain, but they're just in different positions. And so the easiest one to think about for this one is just cis-trans isomerization, that where you get, where it goes from a cis, this using an acid catalyst, it'll actually, it will rotate around and then reform the double bond to lock it into the trans form. So here you've got 2 molecules coming in to make one. Here you've got one molecule that's rearranging. Okay, so those are the basic types. So there's a couple of different ways that you can break bonds. 99% of the time we're going to be dealing with what are called heterolytic cleavage, and that's where both electrons go onto one atom. Okay, so remember there's 2 electrons here, right? So these 2 electrons end up going onto the leaving group here, and so these 2 electrons become this new set of lone pairs, and then what's left is missing a bond. Like that. So if this would say the bromine would go away, and the carbon would have a formal negative charge, because now it only has 3 bonds, while the leaving group here, so let's say it's a bromine, right, it's got 4 sets of lone pairs, so formally it's got a -1 charge. You can have homolytic cleavage, right, where the two, remember you've got the 2 electrons in the bond, one goes on one atom, one goes on the other. Okay, so this one ends up going on the carbon, this one goes on to the other atom, so you're both left with 1 electron systems. So these are what are called radicals. We don't deal with that, we don't deal with them that often, but you do need to know. And if you look at, if you notice the arrows, notice how the arrows are saying this one is going up here, right? But it's a single barbed arrow, which means we're only dealing with one electron is going here, 1 electron is going onto that carbon. We were doing the heterolytic, right? We had a double barbed arrow, meaning 2 electrons were actually moving over. So, okay. So for this one, right, so that when we're trying to make a bond, it's just the opposite. We're going to be tracking where the electrons go, right? So it's not that, so it's always going to be negative to positive. Okay, now it doesn't necessarily mean to be full negative, but it's something with negative character is going to be attacking, making a bond to the carbon. Something that has at least a formal positive charge or partial positive. And with the arrows, what we're doing is we're showing it's sort of a GPS type thing, right? You start, because it's tracking where the electrons itself are going. Where do they stop or start, and where do they go? They go from here to there to make this new bond. So here are those two electrons from the lone pair to make this new bond. So we're going to be making this in between, making this new bond here. Okay, and so you can always think about sort of electron rich attacking electron poor. So the rich attacks the poor. Okay, now you could do this with radical reactions where you have unpaired electrons, right? So this one, this carbon here can use this one electron to combine with the lone electron on this bromine, and they're going to meet in the middle, and they're going to make a bond. So remember, there's still going to be two electrons, one from each one, but now they're sharing them, and so now there's a bond. Okay? But again, notice how with the arrow they're only single barbed, and they're meeting in the middle. Okay, so we're going to use the terminology nucleophile and electrophile quite a bit with this. So you sort of have to think about sort of wrap your head, this kind of a weird logic here. So nucleo, right? It's the same root as nuclear, right? It's positive, right? Things that are positive. Phile meaning loving. So if you are nuclear loving, meaning you're loving a positive charge, that means you are negative. Okay, so we've got this positive or negatively charged base. Say that's going to be our nucleophile. So that it's got a lone pair. It has a negative charge or partial negative or negative character to it. It's going to be attracted to things that have either positive or positive character to them. Okay, and it's going to use its electrons to make a new bond to the carbon. But here the carbon can't have 4 bonds, so it's got to get rid of one, so it pushes these electrons up onto the oxygen. So we don't have to break any more bonds to make here. So these lone pairs here became this new bond here, okay. And then this bond here became this new set of lone pairs. So okay, but the nucleophile is the one that does the attacking. It's negatively charged. It's seeking out positive charge. It is seeking out the nuclear. Right? And just the opposite is what are called electrophiles, right? So electro, right, being the same root as electron for negative loving. So if you are loving electrons, that means you are seeking them. So that means you have to be positively charged. So a carbocation is a classic electrophile. It wants to have it's seeking out negative charge. So we'll be using this nucleophile electrophile quite a bit. So nucleophiles attack electrophiles. Okay, switching gears a little bit, we're going to talk a little bit about thermodynamics. It's not anything, we're just going to talk just enough to remind you about this. Hopefully you saw this in general chemistry. If you want to take a deep dive, you could take a physical chemistry course about that, and they will talk all about this, stuff like that. So, but I just want to talk a little bit about, just as a reminder. So for here, is the reaction spontaneous? Okay. So for that one, what we need to do is we need to look at the Gibbs free energy of the overall system. If the system is the energy drops, right, that means it's going to happen. So like that. So if it goes up, so it gains free energy, that's not going to happen spontaneously. With that, and so you can think the way that I always think about it is your checking account balance, right? So if it just spontaneously goes down, amazingly how that goes, it just seems to go down all by itself, but it takes a lot of energy, and it definitely does not spontaneously go up. Okay? So that's how I keep that's how I keep track of these. Now you can also look at the equilibrium. Okay, so remember it's the concentration of the products divided by the concentrations of the reactants. So if you're at equilibrium, okay, so if the equilibrium is greater than 1, okay, that means the product, you have a lot of products and not a whole lot of reactants. That means the reaction's proceeding forward, right? So if this was 10 and this was 1, right, the equilibrium would be 10. Because you got a lot of products, not very reactants. So if it's less than 1, so let's say it's 1 to 10, then the equilibrium would be 0.1. So if it's below 1, that means it's the reaction actually favors the reactants. So you can look at the equilibrium, you can look at the delta G, and they track very similarly. Okay? So with these, so we can use these things to, we can use what are called energy diagrams and transition states, things like that, to be able to sort of visualize what's going on. Okay, so you start off with your reactants here, and there's some sort of arbitrary energy, stuff like that. And so the first thing we have to do is we have to break this carbon-carbon bond, as well as breaking the bromine. Okay, now we are going to get a little energy back as we add the hydrogen, but we have, as we're breaking the bond, okay, breaking these bonds, it's going to cost us energy. Right? So, so we have to put energy in, and we're going to end up at a state that's not particularly stable. Okay, it's a less stable state than what we started with, and the hump that we have to get over, that's what's called the activation energy. Okay, so this transition state here, this is where you break, the bond is stretching out. This bond is breaking here. We're trying to make it reaching out, breaking that bond. It's a very high energy state. Now, once we make the new carbon-hydrogen bond, we get a little bit of that back, something like that. And so we're at this carbocation intermediate here. Okay, so about that, and so it would look like, so the transition state would look kind of like this, where we're breaking this bond, or actually we're actually breaking that bond. We're actually forming this bond. Okay, but we're breaking that bond. Break this bond. We're forming this bond. About that, and so it's going to cost us a lot of energy. So the activation energy is going to be the highest peak for the highest peak in the transition state. Okay, so at the highest energy structure. So that the larger the delta G, right, the slower the reaction. The delta G, and this is what's called a double dagger. So the higher the delta G double dagger, the slower the reaction. Right, it's going to take you a lot longer to climb over a mountain than it is to climb over a hill. Right? So this is what determines the rate of reaction. Okay, so is how high the transition state is. Okay, and so for these guys here, right? So this one is so if you look at delta G 0 overall, okay. These guys here are non-spontaneous, right? Because it's going up, right? So up, up. Okay, so this is non-spontaneous. Okay, but this one here, this one's going down, down. So these two are going to be spontaneous. So that one and that one. Really terrible arrows. Now, if we're going to talk about speed, okay, it's all about the delta G double dagger, right? Okay, so these guys are going to be fast because the delta G double dagger, the activation energy is pretty low, but these are going to be slow because the delta G double dagger is quite high, so it needs a lot of energy. It's going to take a long time to get over here. So you have to remember that activation energy speed, okay, is not the same as is it spontaneous or not. So just keep those in mind. Okay? So here, so for these two on top, it favors the products. Here, down here, it favors the reactants. But these two are fast, these two are slow. Okay. So the intermediates, okay, that's where we get these little dips. Okay, so that's where you can't isolate these things. Okay, but because they're too high of energy, but they you can detect them with it, and so so for example here, this intermediate is right here where you have the carbocation formed. Before, so as you're bringing this in, it's going to take some energy to deal with the sterics of getting this into proper place, right? So it's a little bit of an activation energy, but when you make the bond, you release a bunch of energy, and so the overall delta G for this is actually quite high, pretty good, right? So because it's going down, so it's a spontaneous reaction. So you can have multiple intermediates in transition states. Let me see if you have it. Nope. So you could have a situation where you start here, right? You go like that. Right here, actually. Like this. Okay, this is a really terrible drawing, but you know, bear with me. Okay, and so this is, so if this is where we start and this is where we end, right, delta G0, right, is negative, right, and so this is supposed to be a G. So this is spontaneous. Okay, now as far as the activation energy goes, okay, we're going to look at this transition state, and this transition state. Okay, whatever the highest one is, right, is going to be the activation energy. And so in this case, it's right here. So delta G double dagger, right? So that it doesn't have to be the first one. It just has to be the highest, right? So the way to think about it is if you're going to hike, you know, the Himalayas, right? So nobody really cares about the smaller mountains you go to. They only care about if you climbed Everest, right? So they don't care about all the smaller mountains you had to climb, right? So for here, all we really care about is that second, you know, in this case, whatever the highest peak is, okay, relative to the starting material, okay. But these are both, you know, so this one has 2 intermediates, has 3 transition states, right? This is where we started, this is where we ended. Okay, so kinetic versus thermodynamic control. Okay, so this is a way that what chemists have realized is that if you mess around with the temperature, you can actually go in and fine-tune which product it is that you're going to be making. Okay, and so for this one, it turns out that if you run a reaction, you know, let's say you get 2 possible products. Okay, this is an addition reaction, but at low temperature, this is the this one actually accumulates. Okay, so you have the H here and the H here and the Br here. But if you increase the temperature, right, so with that you actually get the H here and the bromine way over here. So with that, and so what happens is under low energy under low temperature conditions, right? So you're running under kinetic control, and under high temperature conditions, you're going to be at thermodynamic control. So this is the thermodynamic product, and that's the kinetic product there. Now, what's going on here? So to see the visual, okay, so let's say the first, you're in this, intermediate here. You've got 2 choices, okay? You can go over a smaller hump, okay, that leads to this product here, okay? So this is the kinetic product. This is the thermal product. Okay, so what's happening is if you don't have enough energy to get over the larger of the humps, okay, you're going to take what you can get. Okay, you're going to go up here, you're going to get this little bit, because again, you're going to be going down in energy. You're getting some benefit out of it. Okay, but what you really want to do is if you have enough energy or enough time, you can come in here and you can actually get over this big hump and get down to this very, very low one right here. So the best way that I've described it is I usually do food analogies, right? So let's say you've got 2 grandmothers that live close to you, right? One of them is a block away, the other one's, you know, a mile or 2 away, okay? Say 2 miles away, but easy to walk to, okay? So the one that is close to you will always give you a cookie, okay? But the one that lives far away will give you a nice pie a la mode, right? So that nice warm pie, nice scoop of ice cream. Oh, it's great. But if you only have a couple of minutes to spare, okay, you can run down to the grandmother, right, and get a cookie. Yeah, that's fine, right? So because it's quick, right? But the only way that you can go and get the pie is if you have a lot of time. If you have a lot of time and a lot of energy, that you can get all the way over to the other grandmother's house and back, right? And so this is right. So if you don't have much time, right? You're going to take what you can get and go here. And this is the kinetic product because it has a much smaller the activation energy to get to this product. It's still good. You still drop in delta G. So it's still okay thermodynamically, but what you really want is to be able to spend a lot of energy, which is what you can do, right? If you heat it up, in order to be able to get rid of the bigger hump, in order to be able to get down to this thermodynamic product. So under low temperature, you're going to make the kinetic product. Under high temperature, you're going to make the thermodynamic product. Okay, so catalysts. Okay, so these are either traditional catalysts or biological catalysts for enzymes, stuff like that. So they don't mess with the delta G zero, right? They don't the overall energetics. If it's a non-spontaneous reaction, if it favors the reactants, the enzyme isn't going to help with that. It only helps with speed, okay? Because we're not going to be using. Remember, it doesn't use it up. So what it's doing is it's providing an alternate pathway over the hill, okay, over that activation energy. So it's the difference between going over the hill or going through the hill. So that's all it does. It just speeds up the reaction, and it does that by dropping the delta G double dagger, the activation energy. Okay. Now, this is actually biocatalysis. So when I was in industry, I was actually in a biocatalysis group, and we used either enzymes or microbes to be able to do chemistry. And actually, they offer quite a bit of advantages over traditional chemical catalysts. They can't do everything, but what they do quite well. And the nice thing about biological reactions, when they scale well, and so at very large scale, they can be quite cheap. But you're usually running in water. You're usually running it at either room temperature or slightly above. And they can be very, very specific. They can do they can make a single product very, very specifically. They're also much cheaper, right? One, because you don't have all these solvents to get rid of. Worker safety issue, because it's just usually, again, room temperature, or maybe 37 or something like that. So at body temperature, as well as as you get it, getting microbes or making microbes on large scale is really cheap, right? Just think the beer brewing, something like that. So something like that. And so one of the better examples of this is actually what's called sitagliptin, which is Januvia. This is out of Merck. And so the original process, what they needed to do is turn that ketone into an amine, okay, and a very specific, with it coming out at you on the wedge designs, so it's a very specific stereoisomer. Their original way of doing that is to add ammonium acetate here to turn it into this group here, and then use a very expensive ruthenium catalyst. Some of that, and so this is not only that, the Josephos, these are again these very specific sort of the stereoisomers, and we'll talk about that in chapter 6, or yeah, I think it's chapter 6. I talk about that. But also we're running it. Is that what's called hydrogenation? So it's hydrogen at 250 psi. So you're basically, it's a bomb. So it's like, if you remember the Hindenburg, the blimp that blew up, it was full of hydrogen. And so it's a very, very costly, costly process to be able to do this. And this is the last step, which is exactly when you don't want those processes. So they turn to a biocatalysis route, and you can do this at room temperature, right? Well, slightly at 45, so very hot, but not too bad. Mostly water, and actually you get a much better product here in a single step. So it's a really, really nice process. So again, so remember for this, for arrow pushing, again, if we're dealing with a double-headed arrow, okay, it means we're moving two electrons. So for nucleophilic attack, right? So we're saying the electrons start here and they're going to, going towards the carbon. Okay, just like, with a GPS, right? I'm going to start at home and then I'm going to go and go to McDonald's. Okay, so for that to be able to pick up, go through the drive-through. So for that, and so we're going to make this bond here. Okay. For that, so the other way that we can do it is if we have to do a two-step, where again we've got a negative charge attacking a partial positive, but when that happens, right, when we make that bond there, right, carbon can't have 4 bonds, and so the easiest way to do it, instead of breaking one of these single bonds, if we push these electrons up, we can have that form a new lone pair here. Oops, let me do a different color. So this lone pair becomes this new bond here, and then this bond here, this double bond, these electrons form this new lone pair there. We're not going to have it where this comes in and is dangling and then move it up, because this carbon has 1, 2, 3, 4, 5 bonds. Carbon can't have 5 bonds, so this is not going to work. Okay, we got to get rid of that. If we're making a new 4th bond, we got to get rid of one of the bonds, and the easiest way to do that is to push those electrons off onto something else, either an oxygen or a leaving group or whatnot. Okay, so one of the, and I'm going to draw this in here, there is a hydrogen here, don't forget. So one of the things that can happen is we can have what's called a leaving group, which leaves, and when it leaves, it takes the electrons with it. Okay, so remember there's 2 electrons here. Okay, those 2 electrons, because the bromine is electronegative, they're going to want to go with the bromine, and so these 2 electrons are going to form this new lone pair here. How about that? So, and then the carbon that's left behind, right, only has 3 bonds, so it has a formal plus charge. This is pretty slow, but it does happen. So the other thing that we can do is we can move hydrogens around. Okay, so this is right. So this is partial negative, partial positive, right? So by that, and so this negative, right? And even though this has a formal positive charge, it does have a negative character to it, because it's oxygen's electronegative. It wants electrons, okay? And so if this hydrogen takes this hydrogen here, hydrogen only needs 1 bond, and so these 2 electrons can come down. These 2 electrons, right, can come down and form this second set of lone pairs, and now the hydrogen here. And so here, this bond, these electrons here, this lone pair becomes this new bond with the hydrogen. Okay, you can also do it like this. This is exactly the same thing, right? So this lone pair is going to make a bond here, right? Because you can sort of think of this as partial positive, partial negative. So this bond here, or this lone pair here, becomes this new bond here, right? And then the 2 electrons that are in this bond form this new set of lone pairs. Okay, so this one is not really much different than we were doing before. It's just a hydrogen moving around. Okay, good luck.